human facsimiles that obey the commands of others and also think for themselves. That's the way Hollywood science fiction films portray robots. But that isn't the case in the real world, at least not yet. Robot performance today is impressive. In fact, robots have replaced human workers in a wide variety of repetitive precision tasks on the world's assembly lines.
A robot is just a machine with some intelligence. That intelligence is given to it by a human being through some kind of computer programming. A robot should be able to move itself or other objects. And also a robot should have sensors to sense its environment and be able to react to what it senses according to the intelligence in its program.
Angela Wu, mathematician and professor of computer sciences at the American University.
For example, you can have a dumb stamping machine that simply goes stamp, stamp, and stamp. Even though the paper it's trying to stamp on may be torn or crooked. But an intelligent robot should be able to sense that something is wrong and make corrections. For example, it may try to reposition the paper or throw away the torn paper or go and get another stack of paper if it runs out. So depending on how much intelligence you want to give it, then it will do different things.
At Thomas Jefferson High School, in the Virginia suburbs of Washington, D.C., students in the robotics laboratory are using mathematics, particularly geometry, to work with the design and engineering of robots. Some in simple ways, and others with a bit more ambitious ideas.
It's already here and already there. Here, already there, already everywhere, already ready. So it's McDonald's and a robot.
Oops. It seems the more ambitious you get, the more chance there is for the unexpected.
There is no such thing as a bad robot, just a misprogrammed one.
The student who programmed Hero the robot clearly did not tell him to dump his transistor board on the floor. In fact, John Franklin, a high school senior at Thomas Jefferson, is working on a mathematical model of motion planning to get Hero to perform a much more useful function.
What I intended to do was set it up so that we could tell it to do things and it would be able to do it. For instance, if we told it to go and get a Coke, there'd be 50 cents on a table, and it would be able to get the 50 cents, go down to the Coke machine, buy the soda, and then bring it back to us and give it to us, or set it on the table next to us.
Ready, ready, ready.
Patience, Hero. Let's first ask a mathematician what information you need before you can solve this problem.
A robot should be intelligent enough such that if you give it a floor plan, it should be able to plan a path from any starting point to a goal. But don't forget, a robot doesn't have the full capability of a human being. So in order to plan its path, it needs certain reference points. From the floor plan, its program will tell it how to construct a visibility graph, which has the corners of the objects as the reference points. In graph theory terms, we call those corners and reference points nodes or vertices.
Ready.
From any one node, from any one of the reference points, it knows the points it can reach directly. Those are the points that's visible to the robot from that point. And the distance it has to travel to reach each one of those points. This will form the edges of the graph. Now, from this visibility graph, Hero can decide to move from this point to that point and to another point and eventually reach the goal. This is one path it can take, and we add up the distances along the edges. Oh, the distance is 35. Or hero can decide to go it the other way, and if you look at this path, the distance is 42. So of course, we would like to have a way for hero to plan the best path, namely the one that has the shortest distance. And sometimes we call that the shortest cost. One of the ways for hero to plan the best path, most efficient path, is to use the Dijkstra's algorithm, which is a method a mathematician, Dijkstra, discovered and published in a math journal in 1954. It analyzes the distances between the points, between the nodes, and also use the structure of the graph to find the shortest path from any starting point to any goal.
Jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Hey.
Concentrate, hero, or you'll never get to the Coke machine before the holidays. Is distance your only consideration? Let's ask our mathematician.
No, distance is not the only factor that affects the cost or the time it takes hero to go from one point to another. For example, the distance between 2 points may be shorter, but maybe the floor is bumpy, and hero might have to walk around it a little bit. Or hero, to go from this point to point A, might have to turn a wider angle than to go to point B. So the time it takes for turning and going through bumpy floors and so on will add to the time and the cost of going from one point to another. Luckily, Dijkstra's algorithm will work for costs also. So instead of labeling the edges with the distances between 2 points, you can label it with the cost.
Okay, so let's imagine now that hero has found the best path through the hallway to the vending machine. What next?
Hello, my name is Hero. I think you are cute.
Hero must determine the degree and angle its arm and wrist must rotate in order to reach the slot on the soda machine. And he can calculate that from the length of his arm and its wrist and the coordinate of the slot. Let us assume that he can rotate his wrist and his arm both 360 degrees. If we were to place hero next to the soda machine and we draw in all the places hero could reach, it would look like this, a donut, what the mathematicians would call a one-hole torus. Let me explain why it is a one-hole torus. At any position, if hero rotates his wrist, he can reach any point on a circle, on this circle. Now, if we rotate his arm, then this circle moves, he can reach then every point on the torus. Given the coordinate of the slot, we can tell if his point is on the torus or not. Since the lengths of the limbs are fixed, then mathematicians can write equations to determine the angles that hero must rotate its arm and its wrist in order for it to reach the slot. And we can put those equations into the computer program we give to hero. And then he can do the calculations and figure out the angles it has to move his arm and the angle it has to move his wrist in order to reach that slot.
It should move its forearm forward some, and as it does that, move the upper arm forward and move the forearm downward in order to get to that point.
There are many other problems. For example, we assume that hero can rotate its wrist and its arm a full 360 degrees. But in reality, that cannot be so, because if hero tries to rotate 360 degrees his wrist, then his wrist is going to hit his arm. And also, when hero swings his arm and his wrist up in order to reach the slot, he may hit some obstacles in between. And for example, if the machine is right in front of it and he raises his arm, he may knock a hole in the machine. So these are many of the considerations that we have to consider and put into Hero's program. But once it's in Hero's program, he can deal with all of these problems.
It's already here and already there. Here, already there, already everywhere, already ready. Old McDonald's had a robot. E-I-E-I-O.
As for the future, will real robots ever be a match for the Hollywood fantasy?
There are still many, many problems in the field of robotics that needs computer scientists, mathematicians, and engineers to work together in order to solve them. We need to have people to work on computer vision, speech recognition, path planning, motion control, motion planning. All of these are just some of the problems that we need to solve and have no good solutions yet.
Meanwhile, it's helpful to remember that even in Hollywood, there are some robots who still must learn to take things one step at a time.